we're going to be looking at the derivatives of inverse functions. So let's first look at what is an inverse? So a function g is the inverse of the function f if f of g of x is x for every x in the domain of g. And then same for the backwards. So g of f of x is x for all of x in the domain of f. And then we use this notation for inverse, this -1, almost like it's in an exponent there. So let's use this table to fill in some values and answer some questions. So we have x, and then we have f of x, and then we have g of x, and we want to fill out the inverse. So there's this thing called the reflective property that if on f of x there is a point a, b, when we do the inverse, the point is now b, a, because all of the inputs switch with the outputs. Right? So instead of x being, or the point being 3, 2, the point would actually be, and I'm going to put in a point here, it's going to be 2, 3, right? And then instead of 1, -1, the point would be -1, 1. And then we flip-flop it here as well. Instead of -1, 4, it's now 4, -1. And then the same for the g of x, okay? So instead of 3, -1, it is now -1, 3. And then instead of 1, 0, it is now 0, 1. And then instead of -1, 3, it's now 3, -1. Right, so now let's find some values. So we want to find f of g inverse of 0. So let's do the inside first and do g inverse of 0 and find that. So here's my inverse, and of 0 being the input, I want an output of 1. And now I'll do f of 1, which is -1. Then we can do the same thing for the next, do the inside first, and do that f of -1, which is 4. And then we can do the inverse at 4. So inverse, and the input is 4, so the output of -1. And then we'll do it again. Do the inverse of g at -1. So inside is going to give me 3. But now I need the inverse of f at 3. But I don't have that. I have it at 2, -1, and 4. So this is not defined. And because that one piece is, that entire question, we would say, is not defined or undefined. I wouldn't say doesn't exist, because I guess it's possible it could exist, but it's just not defined in what we have. Let's see this last one. So inverse of f at 4 is -1. So now I want inverse of g at -1, which will give me 3. Right? So let's talk about the existence of an inverse function. So for an inverse to have a function, like when we find the inverse, and for that inverse to be a function, it has to be 1-to-1. So it has to pass that vertical line test and the horizontal line test. Or if we know a function is strictly monotonic across its entire domain, which means it's either increasing the whole time or decreasing the whole time, then that would mean it's 1-to-1, and that would mean the inverse is a function. So let's kind of look at this right here. So let's look at this relationship between the composite function and its inverse. And then I think if we use the chain rule and differentiate both sides, we might be able to come up with a generic formula to find the derivative of an inverse. So let's just let G be that inverse of f. So if I do a substitution, this is now f of g of x equals x, right? So if we differentiate both sides, we'd have to do a chain rule. So we'd have the derivative of the outside times the derivative of the inside, right? And then the derivative over here on this right side of the equal sign is just 1. And then we want to solve for the inside. Since we wanted the derivative of the inverse, this right here is the derivative of the inverse. So we can divide both sides by this piece here. So we get that g prime of x is 1 over, I'm going to use this bottom line, 1 over f prime of g of x. I'm going to do a substitution and say 1 over f prime. And instead of g of x, I'm going to put it back that inverse notation, right? And there we have a generic formula for the derivative of an inverse. So let's see if we can apply that to an example here. So let's see, we have a function, right? 4x minus 3. We know the derivative at 2 is 4. So let's find the value of the derivative of the inverse at 5. So this 5 is actually the output of the original, right? So let's solve for what the x value would be. So we got 5. So okay, we could add 3 and then divide by 2. All right, so we have a point here, 2, 5. On the inverse, that's going to be 5, 2. So what we're finding is the inverse at 5, right? So then we can find the derivative, right? The derivative of f is just going to be 4. But we kind of already knew that because f prime of 2 is 4, which it gave us. All right, so if we use our formula for the inverse derivative, right? So we've got inverse at 5, but we want the derivative of that. That formula was 1 over the inverse, or the derivative of the inverse, right? So we know that our derivative at 2 is 4. So we are just substituting in our value, right? The inverse at 5 is 2. And then the derivative at 2 is 4. And then something to notice is 4 and 1/4. They are reciprocals. So that's a little fun fact. Slopes of inverses are reciprocals. Right, so if we want some nice laid out steps here, so let's let f and g be inverse functions such that f of g of x is x and g of f of x is x, where f of a is b and where g of b is a. So they're inverses of each other. So if we want to find a derivative at a certain point, so or the derivative of the inverse at a certain point, right? First, we want to find the derivative of f. If we're only given the point b, we can find a so that we actually have our point we're looking for, because once we find our derivative of f, we can substitute in a, and then remember our slopes are reciprocals of each other. So let's do another example here. So we have, let g be the inverse of f. Calculate the derivative of the inverse at -9 for the function 4x cubed plus 5x. So we're only given that b value. I want the point a, b. Remember, b is the y value of the original function. So I have 4x cubed plus 5x equals -9, right? So I want to try and solve here and see what we can do. So let's make that a 4x cubed plus 5x plus 9 equals 0. All right, let's try and find some zeros. We can use our pre-calc knowledge and do our P over Q, right? P, Q, and then we can do P over Q and find some values, right? So P is 9, so my factors are plus minus 3, right? And then Q is 4, so my values are 1, 2, and 4. And I can list off all my potential ones, right? Oh my gosh, I forgot my 1 and my 9. So I've got 1, 1/2, 1/4, and then 3, 3/2, 3/4, 9, 9/2, 9/4. And then I can try and just start dividing some out. Let's start with 1. So 4x cubed, 0x squared, 5x, and 9. So that's 4. Oh, but that'll be adding. So no. Let's try -1. And, oh, what am I am going crazy. That's -4. So that's -4. That's 4. That's 9. -9, 0. So, okay. I have a factor of x plus 1, which means a 0 of -1. And this would be 4x squared minus 4x plus 9. And I can check my discriminant, my b squared minus 4ac. So b squared minus 4ac, and I see that this number is going to be larger than this. So I'm going to have the square root of a negative number, which will mean not real solutions. So I only need that one. So my point, we know the y value is -9, so the a value is -1. So then what I need to find now is f prime of x. So that's going to give me 12x squared plus 5. And then I can plug in my -1. And so that's going to give me 12 plus 5, which is 17. And remember, the inverse derivatives, they're reciprocals. So if I'm doing it at -9, that's going to be 1 over 17 as my derivative there, right? All right, let's do some inverse trig. So I have a reminder of some trig functions. I know we've talked before about the main trig ones here, but I went ahead and listed the other three we hadn't talked about previously. So the derivative of cosecant is negative cosecant cotangent. For secant, it's secant tangent. And then cotangent, negative cosecant squared. Okay. And we can do chain rules with all of these as well. All right, so here is listed the derivatives for the inverse trig functions. So I've got inverse sine. The derivative is 1 over the square root of 1 minus x squared. For the inverse cosine, negative 1 over the square root of 1 minus x squared. All right, so on and so forth. I won't read them all to you. So let's just run through some examples using it. Right, it's the best way to go through them. And once we do implicit differentiation, I think we could prove some of these derivatives with triangles. I think that would be fun. All right, so inverse sine. We can go from a triangle perspective. We do have to do a chain rule here, right? So if we think about our chain rule and being the inside, right? So u is going to be 5x. So that means our derivative, so du, is going to be 5. And then we probably, because of the way these are here, right, they all have x squareds in them, we probably have to do some form of u squared. So if u is 5x, then u squared is going to be 25x squared. Okay. So if we say this angle here is u, sine is always opposite over hypotenuse. So if u is 5x, we're going to have 5x over 1. And then we could do Pythagorean theorem here, right? It would be the square root of 1 minus this side length squared, which is that 25x squared, right? So then inverse sine, instead of being opposite over hypotenuse, it's going to be hypotenuse over opposite, right? So y prime. I like that I put examples. I didn't even say any directions. I'm going to differentiate. So 1 over the square root of 1 minus 25x squared. But then because we have to do a chain rule, we got to multiply by the derivative of the inside, which is 5. So really we have 5 over the square root of 1 minus 25x squared. Right? So we can go from a triangle perspective. We're just using our formulas. So inverse tangent is going to be 1 over 1 plus x squared. So we have another chain rule here. We can say that this is inverse tangent of 2x plus 1 to the 1/2. Right? So u, in this case, is going to be the 2x plus 1 to the 1/2. So the derivative is we're gonna need a chain rule here. Chain within a chain. So 1/2, 2x plus 1 to the negative 1/2 times the derivative of the inside, which is going to be 2. The 1/2 times 2 will be 1, so that gives me 1 over the square root of 2x plus 1. All right, and then what do we have here? We have to also find u squared. So I can take u and square it, right? It's going to leave me with 2x plus 1. Well, in the formula, it's 1 plus x squared. So really I'll be adding a 1 on top of that. So then my u squared plus 1 is really 2x plus 2, right? So if I try and plug it all together, I have my derivative is 1 over that 2x plus 2, right? But then times this, my derivative of u. So if I put it all together, I have 1 over 2x plus 2 times the square root of 2x plus 1. Right? Do another one. So arc cosine could go from a triangle perspective again and say, all right, here's where u is going to be, and u is x squared, right? So cosine is adjacent over hypotenuse, so x squared over 1, which means this one here is going to be 1 minus this x squared squared, which is x to the 4th, right? So then my derivative of u is 2x, right? And then my u squared is x to the 4th. So then my derivative is going to be that negative 1 over the square root of 1 minus x to the 4th, and then times that derivative of the inside, which is that 2x. So if I clean that up, negative 2x over the square root of 1 minus x to the 4th, right? Look at another one here. Another inverse tangent. So I can do my u is cosine of x, which means my derivative of that inside is negative sine of x. And my u squared is going to be cosine squared. So if I go straight from just plugging in, right, it's 1 plus x squared. So I'd have 1 over 1 plus, let's see, my u squared is cosine squared, and then times my derivative of u, which is negative sine of x. And if I clean that up, we'll have negative sine of x over 1 plus cosine squared of x. All right. Let's do some tangent line stuff here. So extend it just a little further. So find the equation of a tangent line to the graph of the function y equals arctan of x over 2 at the point 2 pi over 4. So we had to find the derivative first. Remember, the derivative at a point is the slope, and I already have my point. So my derivative, I have a u. So u is x over 2, which means my du is just 1/2, right? And then my u squared is going to be x squared over 4. So we'll have 1 over 1 plus x squared over 4 times the 1/2. And then I can just plug in my point, right? So let's just plug in 2. So 1 over 1 plus 2 squared over 4, and all that times 1/2. See what we get here. So 2 squared is 4, so that's going to be 1/2 times 1/2 to give me a slope of 1/4. So y equals the slope, and then x minus the x value plus the the y value. And there's an equation line. Let's try another one. So find dy dx when tangent of 4x minus y equals 4x. All trig functions will disappear in the answer. All right, so I don't have my implicit differentiation rules yet, so I can't use that just yet. So what we can do is I can probably isolate y. So let's take the inverse tangent of both sides. Right? So I'm left with 4x minus y equals inverse tangent of 4x. And then I think I can move some things around. I can add y to the other side and subtract tangent. So I have 4x minus inverse tangent of 4x to give me y. Then I can do a derivative. So that's going to be 4 minus, then inverse tangent. It's that 1 over the 1 plus x squared. In this case, we have 4x. So 4x squared is actually going to be 16x squared. And then times the derivative of that inside, which is 4. And if I clean this up a little bit, I get 4 minus 4 over 1 plus 16x squared. And that is my derivative there. I could clean it up to get it into one fraction, make it nice and pretty. So why don't we go ahead and do that? I'll move over here. Just multiply both of these signs here by the 1 plus 16x squared. So I'll distribute that 4. So I really have 4 plus 64x squared minus 4 all over that common denominator of 1 plus 16x squared. And then 4 minus 4, cancels out. So I'm left with 64x squared over 1 plus 16x squared. That just looks nicer than having it separated out. Let's look at one more here. So let g be the inverse of the function f of x is 2 cosine x from 0 to pi. So find the value of g prime of 1. All right, so we know our function is 2 cosine x. We know 1 is that b value or that y value. So let's find the x value. So if my function is 2 cosine x, I know the output is 1. So let's find x. Got a little ahead of myself there. Divide both sides by 2. We're only looking between 0 and pi. So where is cosine 1/2? And that is when x is pi over 3. So our point is pi over 3, 1. On the inverse, it's 1 pi over 3, right? So let's find the derivative. So f prime of x is negative 2 sine of x. I can substitute in the point, right? Pi over 3. So negative 2 times sine of pi over 3. Well, sine of pi over 3 is square root of 3 over 2. So I'm left with just negative root 3. Remember, inverses have reciprocal slopes. So instead of the slope being negative root 3, the slope is actually, I'm going to put inverse here, 1 over negative root 3. I'm not a fan of radicals in the bottom. So let's get rid of it, and we'll make that a root 3 over 3, and then not forget the negative. All right, and there's that slope. And that is all for inverse functions and derivatives of inverses. So if you have any questions, let me know.